Welcome to lecture 72 on essentials of topology. In this lecture 2, we will continue the study of the concept of Stone-Cech compactification. Begin with, if we are having a topological space X tau, this topological space has a compactification. Then we have shown that this space is always a completely regular space. Question is, if we are taking a completely regular space, that is, if we are beginning with a topological space X tau and this space is completely regular, whether this has a compactification? Answer is yes. We will justify that this space, that is every completely regular space, has a compactification, and that compactification is known as Stone-Cech compactification. Before studying such compactification of a completely regular topological space, let us see a concept that is known as embedding lemma, which we are not proving here, but we will use this for the study of Stone-Cech compactification. What this lemma is: if we are having a topological space X tau, let us take a family of continuous functions. This is collection of fi's from x to closed interval 0 1. Then we say that this family of continuous functions separates points from closed sets if we are taking any element x naught in x and any closed subset f of x which is not containing this x naught, there is a function fj in this family such that fj at x naught is greater than 0 and fj x equal to 0 for all x in f. If we recall what we are studying here, the concept of separation of points from closed sets, it resembles the concept of completely irregular spaces, where we have already seen that if a space x tau is completely regular, then we have a continuous function f from this ex to closed interval 0 1 such that if we are taking this closed set f, then what we have seen that f of x equal to 0 for all x in f, and if this x naught is an element which is not in f, then f of x naught is always equal to 1. So such function exists in case of completely regular spaces. Now coming to the precise statement of embedding lemma, this lemma is stated as if x tau is a T1 space, if this is a family of continuous functions that separate points from closed sets. Note that this is collection of continuous functions from this x to closed interval 0 1. Then the function f from x to the product of these closed intervals, which we will also denote by this closed interval 0 1 power I, where I is the index set, such that fx equal to these components, that is fix, I belongs to I, is an embedding. So what embedding lemma says, actually it makes a guarantee that if we are having a family of continuous functions with the condition that this family is separate points from closed sets, then we can talk about an embedding from X to product of closed intervals. Also, there is a result regarding completely regular spaces, and the proof is from this embedding lemma itself, and it says that a topological space X tau is completely regular if and only if it is homeomorphic to a subspace of the product of closed intervals, that is 0 1 raised to the power I for some index set I. We have only stated the result along with embedding lemma, but we are not proving here. For proof, we refer the book of Munkers. Now, let us use this lemma and try to see the Stone-Cech compactification of a completely regular topological space. So, we are beginning with this theorem, and this theorem makes a guarantee for the existence of compactification of a completely regular space. This theorem is stated as, if we are having a topological space X tau which is completely regular, then there exists a compactification Y tau dash of this topological space X tau having the property that every bounded continuous function f from this space X to set of real numbers extends uniquely to a continuous function from y into r. First, we will discuss about the existence of compactification, and after that we will discuss the uniqueness of this extension. In order to discuss the compactification y tau dash of x tau, what process we will adopt. Actually, what we will see that first we will discuss about the existence of embedding, and how to talk about the existence of embedding. Why not use embedding lemma? So we are going to use embedding lemma here, and after by using this lemma we will use the lemma discussed in the previous lecture. For extension of this f. So let us begin with the proof. What we have with us are, let us take a family that is fi, I belongs to I, and this we are using just to use the concept of embedding lemma here. So let us take that this be a collection of all bounded continuous real valued functions on X. That is, we are taking the collection of all functions. These are bounded plus continuous, and these are functions from X to R. Now, what we can do that for all I in I, let us choose a closed interval, because we have already used this I for index set. So we are using a different notation for an interval, that is, let us take this interval as ji. This is containing this fix, that is image of x under this function fi, because we are talking about for all I in I. And how to define this closed interval? This is defined as this is nothing but infimum of this fi x and one index supremum of fi x, and we can talk it because we are talking about these bounded continuous real value functions. Now with this interval, let us define a function. So how to define a function? We are defining a function h from this topological space x2 product of these closed intervals, that is ji, I belongs to index set. How to define it? We are defining in this way that this hx is precisely the components are given as fi x, I belongs to I. It is to be noted here that when we are talking about this product, every closed interval is compact, and therefore by using Tikhonov theorem this product is also compact. So this is because of the well known Tikhonov theorem. Now as this topological space x tau is completely regular space, so from here what we can deduce that because this family what we have taken here I belongs to I, this will separate points from closed subsets of x. And if this is the case, now we can use embedding lemma, and by using embedding lemma we can conclude that h is an embedding. Now let us take this y tau as this is a compactification of this topological space x tau. This is induced by this embedding h. Then if we are using the lemma which we have discussed in the previous lecture, what we can say that there exists, and this is because of lemma discussed in previous lecture. We can say that there exists an embedding let us take that embedding as h. This is a map from y to product of these closed intervals I belongs to y, such that this embedding has a property that h of x will always equal to this hx for all x in x. Now what we have assumed, we have a function f from x to r. It is to be noted that what this function is, this is bounded continuous. Obviously this is real value, so this is a bounded continuous real valued function, and if it is the case we can say that f is a member of this family of functions, that is fi, I belongs to I, and if f is a member of this family we can assume that this f is something like fk for some k in the index set I. Now, if we have this f as fk, we can talk about the projection map is phi k from the product of these closed intervals, that is ji, I belongs to I, to this interval, let us take gk. It is to be noted that this projection map is always continuous. Now, what we can talk? We can talk a function from y to jk, and that jk is subset of R. How we can talk about it? Answer is here, because from y to this product of closed intervals ji, I in I, we have a continuous function h, and from this product to jk, we have this projection map phi k. So precisely from y to jk, we have a function that is pi k composition this h. It is to be noted that this h is continuous and pi k is also continuous. Therefore, what this function is, this is a continuous function, and actually this is precisely the extension which we require, because if we are computing this pi k composition h at any x where x is an element of this x, this will be nothing but this pi k of h of x, that is given by pi k hx. And if you recall the definition of hx or definition of h, what we have already defined, that this hx is nothing but f I x where I in I. What we can conclude from here, that this is pi k of this is f I x I in I, and because this pi k is a projection map, this is precisely fkx, and it is to be noted that what fk is nothing but the function f itself. Therefore, this is f of x. So this is a function, or this is a continuous function which extend the function f from x to r. And it is to be noted that if such extension exists, what this y tau dash is, we call this space y tau dash. This is precisely the Stone-Cech compactification of topological space x tau, and the standard notation is given as this is beta x, and let us put this topology tau dash as these topological spaces, or a topological space x tau is noted simply by x. So people use the notation that is beta x to denote the Stone-Cech compactification of a topological space x tau. Thus we have shown the extension of this function f. Only we have to show that this extension is unique. We will justify the uniqueness by using a result. The result is stated as, if we are having two topological spaces, one is x tau and second one is z tau dash, where this is a host of topological space. If we are taking a subset A of x, and let us take continuous function f from A to z, then there is at most one extension of f to a continuous function g from closure of A to Z. It is to be noted that uniqueness in our case will follow by taking Z is equal to R and A is equal to X. Now let us prove this result. So what we are assuming that, for example, if possible, why not let us take, let there are two extensions of this A. So G and G dash are two maps from closure of A to Z. These are continuous functions and these extend F, and we are taking these two as different. Now what will happen if these two are different? So there exists at least one X in closure of A, so that this Gx is not equal to G dash X. But at the same time, it is to be noted that this Gx and G dash X are elements of Z. And what this Z is? This space is Hausdorff. So what we can take, because this Z with this topology tau dash is Hausdorff, what we can conclude that there exist two open subsets of Z. So let us take these open subsets G and H of Z, such that what we can conclude that one is containing this Gx, that is Gx belongs to G, this G dash X belongs to H, and finally this G intersection H is empty set. Now let us take an open subset, for example O. So this is open set, and this open set is containing X, and this is having feature that this GO is subset of G, and this G dash O is contained in H. Can we take it? Answer is yes, because G is continuous. Now because this O is an open set containing X, so X is an element of O. At the same time, X is an element of this closure of A. So what we can conclude from here, that this O intersection A is non-empty. And if this is non-empty, why not let us choose an element Y in O intersection A. So let us assume it. Now if Y is an element of O, from here what we can conclude? We can conclude that this Gy is an element of G, and this G dash Y is an element of H. At the same time, it is to be noted that Y is an element of A. Because Y is an element of A, therefore what we can say that this Gy is equal to Fy, as well as this G dash Y is also equal to Fy, because G and G dash are extensions of F, and F is defined from A to J. From here what we can conclude? We can conclude that this Gy is equal to G dash Y, and if Gy is equal to G dash Y, note that Gy is an element of G, G dash Y is an element of H. So what we can conclude? We can conclude that this G intersection H is non-empty, contradicting the fact that G and H are disjoint by using Hausdorffness of the topological space Z tau dash. Therefore, this, that is what we have assumed, that there are two different continuous extensions G and G dash from closure of A to Z are not possible. That is, there will be at most one extension of F to a continuous function, that is G, from closure of A to Z. Now let us see one of the property of Stone-Cech compactification, what we have discussed. So begin with a completely regular space. So let us take x tau. This is a completely regular space, and let us assume that this is y. Tau dash is a compactification, as we have discussed in the previous theorem, that we call this Stone-Cech compactification. If this is the case, we can talk about the extension of the function with these assumptions. So let us assume these one. Now what we can deduce that if we are having any continuous function f from ex to c, what this c is actually c with this topology tau double dash is a compact Hausdorff space. The function f extends uniquely to a continuous function g from y to this compact Hausdorff space C. In order to prove it, let us begin with this space, that is C. Tau double dash. This is given that this space is a compact Hausdorff space. We have already discussed that every compact Hausdorff space is normal and every normal space is completely regular. So what this C tau double dash is, this is a completely regular topological space. And if this is a completely regular topological space, what result we recall that this topological space can be embedded in this closed interval, that is 0 1 raised to the power I for some index set I. So why not let us take this C as a subset of this product of closed intervals. Now what f we have with us, note that this f is a function from ex to this c, and what c is being completely regular, we have seen that this is a subset of the product of closed intervals. Now if it is the case, what we can say that each component, let us take fi of this function f is bounded. So this is a bounded continuous real valued function on x. So by our assumption from the previous theorem, what we can say that this function fi can be extended to a continuous function. Let us take that continuous function be g I from y to r. It is to be noted that such extension will always be unique. Now having this function gi from y to r corresponding to this fi, what we can define a function g from y to this product of set of reals, that is Ri, such that what or how we are defining this function, we are defining this function as g of y. This is equal to this tuples gi y, where I is an element of I. It is to be noted that what this one is, or what the product of set of reals, this is endowed with product topology, and therefore what we can conclude we can conclude that the function which we are defining here, that is this g, is a continuous function. So we have constructed a continuous function from this set y. Now what we can justify that the image of this y under this g, because this y is compactification of the topological space x tau. So we can write that this is g of closure of x, and because of the continuity of this g, we can say that this is closure of gx. But as g is an extension of f and on x both are same, so this is precisely closure of this fx. And what f is, if we see f is a function from x to this c, so this is precisely closure of c, and that will be nothing but c. So what we can say that this g is a function from y to c, and it is to be noted that this is continuous. Also, its uniqueness follows from the fact that how we have constructed this G, as such Gi are unique. Therefore, actually this G is precisely the required extension. Moving ahead, and if we are taking two such compactifications, y1 tau 1 and y2 tau 2 of a completely regular topological space x tau. So we are taking this space as completely regular. Question is, can we show that such compactifications are such spaces are equivalent? So we can justify that R can be justified that the spaces y1 tau 1 and y2 tau 2 are equivalent. Answer is yes. Just to think on it. These are the references. That's all from this lecture. Thank you.